This is AP Calculus BC, and in this video, I'm going to talk about sections 4.3 and 4.4. In section 4.3, we're going to talk about analyzing functions, and really what's in this section is getting into the idea of graphing functions using all of the information that we've learned in calculus and combining that together with things that you've learned in previous courses. And then we're also going to talk about section 4.4, and in that section, we're going to get into extreme values of functions. And really, we're going to talk about absolute extreme values of functions, meaning an absolute maximum or an absolute minimum for a function. So in this first section, like I mentioned, what we're trying to do here is piece together everything that we've learned in sections 4.1 and 4.2 and put that together with things that you learned primarily in Algebra 2 about graphing functions. And what we're going to try to do is graph functions like this one. So what really the main purpose of this is we're trying to get the idea that now that we know how to analyze these functions with derivatives, we have a lot more information about how a function is behaving. And where this becomes useful is when we start doing problem solving, we're able to analyze these functions in a much simpler way than we were able to do in the past before we knew how to do this with derivatives. So for this first problem, what they're asking us to do is sketch a graph of this function. And what I'm going to do is I'm going to rewrite this in a factored form, and you'll see why in a second. But 2x squared minus 8, I could factor a 2 out, and then I can factor the remaining x squared minus 4 into x minus 2 times x plus 2. And then in the denominator, obviously, that factors into x minus 4 times x plus 4. Now, the purpose of that is I'm trying to make it a little bit more obvious where some of these main things are going to come from. And what I'm talking about in terms of main things are things that you already know how to do or you did before you came into this course. So vertical asymptotes, for example. I can see now from the denominator that there's going to be vertical asymptotes at x is equal to plus or minus 4. I can also see where the x-intercepts are going to occur. There's going to be x-intercepts when x is equal to plus or minus 2. I can also see the horizontal asymptotes. And in this case, there's only one. That would be at y is equal to 2. And then the last thing that you can definitely just really quickly analyze would be the y-intercept. So remember, that's when x is 0. So the y-intercept would be at the point where y is equal to 1/2. Okay, so those are all of the pieces of information that you could have done back in Algebra 2. So now what we're going to do is combine our calculus information with that information and get a really accurate graph. So I'm going to start by looking at the derivative. And I'm not actually going to take the derivative and go through all the simplifying here. I'm just going to show you what this simplifies down into. So your derivative, if you were to take it, it's negative 48x, and that would be divided by x squared minus 16 squared. Okay, so now if I were to set that equal to 0, obviously x equals 0 is a critical point. But there's two other points I want to make sure that I consider in my sign chart. I know I have vertical asymptotes at 4 and negative 4. So really, those are not considered critical points. But I do want to know how the function is behaving on either side of those vertical asymptotes. So I'm going to make sure in my sign chart to include those points. And so I've got negative 4 here, 0, and then 4. Now, this is pretty easy to analyze because in my derivative, the denominator is always positive. The numerator, if I have a negative number plugged in, the numerator is going to be positive. That's going to make the overall value of the derivative positive. And in a similar way, if I plug a positive number in for x, that's going to make the numerator negative, which is going to give me a negative derivative value. Now, you can see there's actually going to be a maximum at x is 0, and I can see that because my function went from increasing to decreasing at 0. All right, so now let's look at the same thing with the second derivative. With the second derivative, if I were to take the derivative and do all the algebra to simplify it down, it would simplify into 48 times 3x squared plus 16 divided by x squared minus 16 cubed. Now, if you look at that, there's not any points where the second derivative is equal to 0 because 3x squared plus 16 is never going to be 0. But I do still want to test around those vertical asymptotes again because I want to make sure I know what's happening with the concavity of my graph on these regions. So -4 and 4 are included, not because they're necessarily points of inflection. They can't be points of inflection since we have vertical asymptotes, but they are locations where my concavity can change. So when I test around here, you can see that the only way that I'm going to end up with a negative number is if the denominator is negative, because the numerator is always going to be positive. So the denominator is only going to be negative when that x squared value is smaller than 16. And that would happen between -4 and 4. When I'm outside of 4 and -4, or greater than 4 and less than -4, then I'm going to switch to a graph that's concave up. So now I'm going to piece all of that information together, and I'm going to sketch a graph. Now, when you sketch your graphs, these things don't have to be perfect. I've said this before, but I do want you to include all of this key information. So we've got some vertical asymptotes here that I want to make sure I include. So I know I need to go 4 units out to the left. I'm going to try to scale that the same on the left side as I did on the right side. Okay, so then I also know I've got a horizontal asymptote at y equals 2. I know where my y-intercept is. Okay, so now I'm going to put in my asymptotes here. So I've got an asymptote at -4, x equals -4. I've got another one at x is equal to +4. So for x equals +4, I'm out here. There we go. And then I also have a horizontal asymptote at y is equal to 2. So once you have your asymptotes in there, you can kind of see how you've already created regions within the graph, which is what we would expect based on the fact that we have these vertical and horizontal asymptotes. And I'm going to go ahead and label these. This is x is equal to 4. This is x equals -4. And this is y is equal to 2. Okay, we also knew that we had x-intercepts at 2, 0 and -2, 0. And I've got a y-intercept at 0, 1/2. Okay, so we have all of those points. Now, in this middle region, since I have all these points in the middle region, that would be the easiest region for me to plot. Look at my sign charts. You can see that my function should be increasing and then decreasing. It should also be concave down on this entire interval. And that pretty well matches up with what I'm expecting here. You can see how this sort of looks like a quadratic opening down as I plot this in here. So that's my middle region. Now, for the regions outside of 4 and -4, it becomes a little more complicated, but I do know that I'm probably going to be operating within either this section or this section for each piece of the graph, and then same thing over here, either this section or this section. So I'm going to go through and I can just test a point, and that'll tell me what location I need to be in. So for example, if I'm out where x is equal to 5, well, I can tell if x is equal to 5, I'm going to get a number that is greater than 2. So that's going to give me a value that's somewhere in this region up here. So I know my graph is going to generally have that shape. And then the same thing, I could plug in -5. It's going to give me the same value, and I know I'm going to operate in that region. So now I've got a pretty accurate representation of what this function is doing. How is it behaving between -4 and 4? How is it behaving when x is greater than 4 or when x is less than -4? And that's really the main idea, is just piecing the new information that you just learned together with the stuff that you've been doing now for a couple of years. Okay, so notice my graph is not perfect. It's not even really that neat, but it's got all of the key information there. And if somebody were to look at that, they can tell what's happening with this function as x increases or as x decreases. And I can see what's happening around the asymptotes. I have all of the key information about this function. Okay, so what I want you to do is try these next 2 questions. And on these next 2 questions, you can see that we're talking about vertical tangents and cusps. You should be able to tell from the function what type of a graph you're dealing with. So you can see on this one, we've got a exponent of 2/3, so obviously that's going to be a cusp. Here I've got an exponent of 1/3, so that should be a vertical tangent. But what I want you to do is try to go through essentially the same process I just went through. Start with your x-intercepts, y-intercepts. You don't have any asymptotes this time. And then use your derivatives and analyze the derivatives. And once you have all of that, then sketch your graph. So I want you to take a couple of minutes, pause the video, and when you come back, I'll show you the solutions for those next two. Okay, so here is the x minus 4 to the 2/3 power. You can see I found my x-intercept and my y-intercept, but then I've got my derivative. I can see there's a critical point at 4. So remember, the original function was defined at 4 this time. So 4 is a critical point, and the function went from decreasing to increasing. When I got my second derivative, you can see that I got negative 2/9 times x minus 4 to the negative 4/3, or negative 2/9 x minus 4 to the 4/3. So that could potentially be positive or negative in the denominator, but when I start looking at having a fourth power, that's going to force everything to become positive. So even though the denominator looks like the expression x minus 4 could be positive or negative, since I'm raising it to the fourth power and taking the cube root, that's always going to make that number positive. So there's nothing I can do that will make that second derivative come out anything but negative, because the denominator can't be negative. So that means my graph's always concave down. And then from there, I can piece together all of that information on my graph. And you can see that I've got a cusp as expected. The graph's concave down, hits that point at 4, 0, and then is still concave down and increasing. All right, for the second one, same idea. This time I went through, I found my y-intercept and my x-intercept. I've got my derivative of 1/3 times x minus 2 to the 2/3 power. Here I've got a critical point when x is 2. With this being a cube root, I kind of know I've got a vertical tangent. So what I'm expecting to see with my actual graph here is I'm expecting to see the shape that I'm accustomed to with a cube root. So you can see when x is less than 2, it's similar to what I have in the last one. I had a mistake here on my sign chart, but you can similar to the last one. Since we're doing x minus 2 to the 2/3 power, that means we're always going to square x minus 2, and then we're going to take the cube root. So that's going to make the denominator always positive. That means that this expression for the derivative always has to be positive, except at 2 where it's undefined. And then the other point that I have here, or the other derivative I have here, is the second derivative. And you can see that my graph goes from concave up to concave down around x is equal to 2. Okay, so as you expect, that's the shape of the graph. It's basically the cube root graph shifted 2 units to the right. Okay, so in terms of how do we do these questions? Here are the things that I want you to be considering when you graph these functions. I want you to make sure that you're considering any symmetries that you might see, x and y intercepts, vertical asymptotes, whether the function's positive or negative, thinking about the end behavior of the graph, and then obviously everything we do with the first and second derivative. Okay, so I don't, like I said before, if I ask you to graph these, I don't expect your graphs to be perfect, but I do want to be able to look at them and at least have a feel for the behavior of the function. All right, so let's move on to section 4.4. And in this section, we're going to talk about absolute max and min values. And this is actually relatively simple to do. However, we have to make sure that we're really clear on when we talk about an absolute max or an absolute min. So when we talk about an absolute maximum or an absolute minimum value, that means there's no function value higher than that value or lower than that value, depending on if you're talking about a maximum or a minimum. So it's pretty easy to see when you look at a graph where an absolute max or an absolute min is. But in terms of, let's say we don't have a graph, well, then what we use is called the extreme value theorem. So the extreme value theorem is when I'm dealing with a closed interval. So a closed interval means that the endpoints of my domain are included in terms of what's my domain of my function. So you can see the brackets around the AB. That means that the point A and the point B are both included in my domain. So you can see it here. So the extreme value theorem is just basically going to tell us that if we are operating on a closed interval and we have a continuous function, then we know that we have to have an absolute max and we have to have an absolute minimum. Okay, so that's the first part of it. Now, the second piece is when I use that extreme value theorem, there's also sort of an offshoot or a corollary to that. And that is that if I know I'm going to have an absolute max or an absolute min on a closed interval, I only have to look at certain points. So the only points where the absolute max or the absolute min could possibly occur would be at the critical points or the endpoints. So let me go back to this graph and just show you that if you look at any of those three graphs, the absolute max or the absolute min always occurs at a critical point or an endpoint. So that's what we call the closed interval method then. We're using the extreme value theorem and combining that with that corollary that we know for sure if we have a function that's continuous on a closed interval, there has to be an absolute max or an absolute min, and it has to occur at a critical point or an endpoint. Okay, so let's go through and talk about how we would actually use this. So this question says, find the absolute maximum and minimum values of this function, it's a cubic function, on the interval -1 to 5, and determine where these values occur, and then justify your answer. This is not difficult to do. Now, notice when it says justify, you might be thinking, okay, well, maybe we're going to have to do some writing here. And the reality is you don't have to do any writing in this scenario. So what I'm going to do, I know this is a continuous function. I know I'm dealing with a closed interval. I'm going to start by finding my critical points. So I'm going to take my derivative. It's 6x squared minus 30x plus 36. And I'm going to set that equal to 0. That's going to give me the values. And I'm not going to go through all of this algebraically, but if you factored it and solved it out, you would get x is equal to 2 and 3 as your critical points. So we have 2 critical points. Now remember, the only points that we have to consider in terms of absolute max and absolute min are our critical points and our endpoints. So I'm going to create a table of values here. And what I'm doing here is called the candidates test, because I have 4 candidates where the absolute max or the absolute min could occur. And those are all my critical points and endpoints. So -1, 2, 3, and 5. So -1 and 5 were the endpoints, 2 and 3 were the critical points. And then I can just find those corresponding function values. Just go back up here to the original function, plug in those x values. And so for -1, you'd get -53. For 2, you get 28. For 3, you get 27. And then for 5, you would get 55. Now remember, these are the only points where the absolute max or the absolute min could occur. So it's pretty clear here. There's my absolute minimum, and here's my absolute maximum. And I can tell because the absolute maximum and the absolute minimum can't be anywhere else except for one of those 4 points. So now I can just write out my solution. So my absolute maximum is going to occur at the point f of 5 is equal to 55. And my absolute minimum is going to occur at the point f of -1 equals -53. Now, you might be concerned because this said, justify your answer. The reality is, I have already justified my answer. I've done everything I need to do on this problem to justify my answer. So by using this candidates test and showing all of these values in this table, what this is doing is it's serving as my justification. It's very clear. I showed here that I'm finding critical points because I set the derivative equal to 0 and I found these values. So clearly those are my critical points. I also included the endpoints in that table. Those are the only points where the absolute max or the absolute min could occur. Since I've tested all those points and from that table I gave those values, I've got everything that I need. I have justified my solution. So on these types of questions, when you have to do or when you have to find extreme values, this is what I expect you to show for your work. This is one of those things that is 100% certain to show up on your AP exam. And I don't like to teach things just to tell you about the AP exam, but there are certain things that have to be formatted in certain ways for the AP exam. And this is one of those things where, yes, I could justify my answer in words, but if I start justifying my answer in words, I'm going to have to account for all 4 of these points. I'm going to have to explain critical points, and then I'm going to have to explain all my reasoning there. But instead of doing my justification in words, I did my justification mathematically by showing that I'm applying the extreme value theorem. Okay, so pretty simple to do, but keep that in mind because that's what I'm going to expect you to do. If you see that on a quiz or a test where you have to show work, that's the work that I would expect to see. All right, so let's take a look at one last problem here. And just really quickly, I've got, just as an aid for you, I've got some graphs here. If you're not really sure about what the graphs are going to look like based on the behavior that you see, this is just a brief summary. And these are all things that you could reason through, but sometimes when you first see these things, it can be helpful to see an actual sketch to understand what they're talking about. So this one's talking about absolute extreme values when you have infinite intervals. And you can see on some of them, we do have absolute extreme values, some of them we don't, and it depends on the end behavior. And then this is also talking about open intervals, whether we're going to have absolute extreme values. And you can see with open intervals, sometimes, again, we will have extreme values, absolute extreme values, and sometimes we won't. And again, it just depends on the behavior of that particular function. But this just gives you a little bit of feel for what you're looking for when we're on open intervals. All right, so last problem here I want you to try. This is an old AP test question, and this is a multiple choice question. So this would have been on obviously the non-calculator section. And I just want you to take a couple of minutes. I want you to pause the video, take a couple of minutes, and try to solve this question out. All right, and here is the solution that you should have ended up with for that one. You can see that what I did here was I took into account the domain of my function. And the reason that's important is because I've got a domain restriction. So because I've got a square root, that means that this 2 minus x expression has to be 0 or greater than 0. So that's where I found this domain, by taking that into account. So I've got that domain restriction. Now I can go through and I can analyze my derivative, but if you notice when you take the derivative, you don't get a ton of information because I know the function is always increasing. So I don't see a change in direction on my graph. But that's actually enough information for me to know what's happening here. So even without knowing the exact shape of the graph, if you just kind of reason through this, the derivative is always positive, my function's always increasing. So think about, regardless of what the shape of the graph is, if I start at some point and I'm always increasing, I'm going to get to the maximum value when I get to that right endpoint. Well, I have this domain that goes from negative infinity to 2, so I know my maximum value is going to occur when I get to the right endpoint of 2. Now, the common mistake that people would make on this question is they would say, oh, well, it occurs at x is 2, so I'm going to circle 2 as my answer. I underlined value in the question intentionally to make it really clear we're not looking for the x value, we're looking for the function value. Whenever the question says find the value or the maximum or minimum value, it's referring to the function value. So you've got to give in this case, the y value. And when I plug x is equal to 2 back into the original function, I get a y value of 0. Okay, now normally you wouldn't have value underlined. It would just say the maximum value of the function, and you would have to realize that that's an important thing to be paying close attention to. So keep that in mind as you work through the problems.